So I wanted to show you some planar examples of projectivities. Now these are supplied by Dr. Peel of the Minnesota State University. So in this left image, use two elementary correspondences, which you should note are called perspectivities despite being between a point and a line, via P first. So we have this starting line containing points A, B, and C, and they're kind of mapped to this axis, P prime, and it's via an elementary correspondence to P. And we have a secondary elementary correspondence through this center, O, that sends each point to this final line. So showing these points, they're actually sent to A double prime, B double prime, and C double prime. Now in the central image, we have a pencil of lines through P, and we intercept each one with a unique line through P prime. So we're kind of intersecting it in this sense, each line through each one of these 3 points. So I believe, and correct me if I'm wrong, that we actually have a perspectivity between P and P prime in this sense. Every pair of corresponding lines, they each meet at some kind of point on O, which is our axis. So I think we can think about it in that sense. They're sent to this other axis, O prime, through an elementary correspondence here. And that sends these points to the line O prime, where we can extend another line through each of these points, A prime, B prime, and C prime, I have labeled them, in order to meet at P double prime. And that generates these final line segments, A double prime, B double prime, and C double prime, as I just showed you. And so that's actually going to be a projectivity between the points P and P double prime. But that's not really why you're here. We need to get to some of the theorems in projective geometry. So one idea you might be getting by now is how many points exactly determine a projectivity? Well, the answer to that question is actually exactly 3. So as you can see on this next paper from actually the same source, this describes the fundamental theorem of projective geometry. And so, as it says, it's sort of underlined here, a projectivity between 2 pencils of points is uniquely determined by 3 pairs of corresponding points. Now we can also take the dual of this theorem, and that's basically saying we can swap pencils of points for being pencils of lines. So really it's saying a projectivity between 2 pencils of lines, i.e. points, is uniquely determined by 3 pairs of line segments, basically. So that's very interesting. You know, a lot of people, well, a lot of mathematicians, people interested in mathematics, very often wonder, you know, what is the precise number of points that defines a line or a circle, or more generally any kind of conic, and we'll get to that later, a polynomial equation, or you know, this type of correspondence or that type of correspondence. Well, in this case, a projectivity, and this is very general, and it's actually the fundamental theorem of projective geometry. Any projectivity whatsoever between 2 lines or 2 points is uniquely determined, so there's only one, between 3 points or 3 lines that correspond to each other. But aside from this fundamental theorem, we're going to begin our kind of tour of many different kinds of theorems with this one right here, which is Pappus's theorem. We will begin our tour in 4th century Alexandria. So Pappus of Alexandria was a prominent geometer of his time, and there are actually several theorems that bear his name. We see it in the Pappus chain, for instance, which may be a topic in a future video, and the centroid theorem, which you can see here. However, we will mainly discuss the Hexagon theorem. What this is really saying, as you can see it highlighted here, is that if we have alternative points of some point hexagon, and that's kind of, this will become important, this point hexagon, later on. We're saying that if alternate points of this point hexagon are incident to 2 fixed lines, so basically, if there are 2 straight lines, each of which holds 3 points, and again, we'll see a diagram in a moment, but we know that opposite sides are incident to 3 collinear points, is how it's worded here. And so There are many kind of results of this theorem. We know it's a generalization of Desargues' theorem, and it turns out they can, these kinds of theorems can be used to generate projective geometry over some kind of field, which we've discussed to a small extent before, but if we would like to see a different kind of an image to describe this, then we can actually see it in figure 7.1. So we can call this a point hexagon, and just simply because there are 6 points in a plane. In this case, it's a somewhat specific kind of hexagon because, of course, we have we have them lying on 2 distinct lines, straight lines. However, it's still very interesting because if we consider these corresponding lines between, for instance, P1 and P6, and P3 and P4 here, then that is one kind of pair of lines whose meet, or intersection, will become important later. We also have from P1 to P2 here, and P4 to P5. So it's this entire thing, this entire corresponding side from 1 to 5 and 2 to 4, which is spanned by these 2 lines in some sense. And then P3 and P5 and P2 and P6, we also have this final pair of lines. And what Pappus' theorem says is that each of these points of intersection are collinear, which is actually very interesting. In fact, this theorem has been praised by Dr. Wildberger, one of my favorite modern mathematicians, as a valuable human accomplishment. But that's not all. There are actually even more developments that come after Pappus' theorem. A very important one that came afterward was Pascals' theorem, which was a certain generalization that came around 1640. Pascal was actually quite a young mathematician at this time. But he generalized it to basically a non-degenerate case. He made it so that it could work in any sort of point conic, basically. So speaking of conics, this is what we'll get into. And so I'd like to kind of draw your attention, just very briefly, to this statement. Looking at things as an artist, this says that any drawing of a conic section is again a conic section. The picture plane is the intersection plane. So this is, a very interesting result, particularly in projective geometry, since we're considering the projection of any conic into some other plane. So basically we're talking about intersecting some kind of cone with a plane, and even if the cone isn't a right circular cone, we can have other instances, but it turns out that the figures generated in a plane, or, the cross-section, so to speak, are still conics. They're conic sections. Very interesting. Now, moving on. Basically, we're considering some of the basics of conics. Many of you will already know this, but a non-degenerate conic would be either an ellipse, parabola, hyperbola, or circle. Those are kind of the 4 general kinds of conic sections. Interestingly enough, there are some degenerate cases which are either, this source says it can be empty, 1 point, 1 line, or 2 line. So technically those are the degenerate cases of conic sections. And also I would like to add my own recommendation, my own kind of insight to this part of it, which would be to say that a circle is technically speaking an ellipse. So considering, I guess, maybe a family tree or some kind of set of categories of conic sections, I would like to make that distinction that a circle has that property where it is a specific type of ellipse, but that, I think, should be emphasized a bit more. And correct me if I'm wrong, but to me it makes most logical sense to say that, if we're striking a cone with a plane, if that figure is still enclosed within that plane, then even if it happens to have a constant radius, that's a special case, but it doesn't mean that it is no longer an ellipse. Anyways, moving on. The projection of a conic section from one plane to another plane is a conic section of the other plane. This is what I was trying to foreshadow earlier. So it says that there's basically a correlation between the algebraic definition and the geometric definition of a conic section. And so there are some interesting results you can see about the point conic. In this case, they're showing the parabola y equals x squared, and how in the projective plane it does actually intersect this line at infinity right here. And basically it intersects it once and only once, and so therefore the line at infinity is actually tangent to this parabola. So that's a very interesting thought to consider, but I said I would move on to some theorems. So, right, again, about Pascal's theorem. We know that if we have a point hexagon lying on a point conic, then the three pairs of opposite sides are, again, incident to three collinear points. So, again, it's kind of a mouthful, but there's a figure to help us understand it. There's a graphic. So in this case, figure 7.4 is describing a line conic, a conic which is kind of bound by all these tangent lines around it, which is again interesting. But figure 7.5 is actually describing Pascal's theorem, which is, we actually have this set of 6 points, as you can imagine, and they lie on this conic, in this case some kind of ellipse. And indeed, the points of intersection of, corresponding, I know I don't have a ruler, so I'll try to make this as neat as I can, of corresponding lines, each of these 3 points, I'm simply trying to say, they are collinear, as you can see. And this works for any kind of point conic on which there are 6 points. So that's certainly very interesting. And in fact, there is a dual version of this theorem developed in 1806 by a mathematician named Branchon. I'm actually not sure how to pronounce that, but you can see it just below here. And it basically is saying if we have a line hexagon lying on a line conic, so it's, again, if we're kind of replacing every point with a line, or at least the notion of a line, then the 3 lines which we're kind of constructing through opposite points of the hexagon are incident with a point. So instead of having 3 points which are kind of lined up and we have, one single line passing through them, it is actually somewhat different from that. What we can actually see is that we have a line conic, or really, I guess, a line hexagon, which serves as our boundary for the line conic, I should say. And these lines across opposite points of this hexagon meet at the same point. That's very interesting. Who would have thought that originally? Well, mathematicians in the 19th century, I suppose. So it's very interesting. But, yeah, I wanted to show you those things so that you knew about them, because they're just truly interesting. They're, genuinely interesting. The one thing I also wanted to show you was, back on this page, the text right below it actually gives us some very good insight. And that is actually the answer to another fundamental question, which is, how many points uniquely determine a conic? We know for a general line, according to Euclid, he postulated that basically there would be 2 and only 2 points that define a line. Well, alright, that makes sense, I suppose. At least in certain context. Well, for a conic, it turns out to be, the number is actually 5. It's exactly 5 points that uniquely determine a conic. As you can see, there is one and only one conic through 5 distinct non-collinear, or non-copunctual, points or lines. This is very interesting. You can even consider taking a piece of paper and simply jotting down 5 non-collinear points, and then simply imagining what kind of conic would be defining these 5 points, or would be defined by these 5 points, I should say. So in my example up here, well, I've tried to draw it so that basically the conic is going to be something like an ellipse as such. Obviously this is just a rough sketch, but of course if we arrange the points in some other way, I'd imagine we would have a different conic. let's say we wanted a parabola, we may be able to say something like this. And I'm sure for a hyperbola we could choose different kind of points as well. But I just wanted to introduce you to these ideas. I submit that people, I would say students, but in reality all people are students, need to lose their inhibitive fears of academic topics. I submit that it is not the least, but rather the most normal, the most human behavior to try to learn new things about points, lines, conics, and numbers. I submit that we should all be more open-minded about topics that are new to us, that we should give respect to those sophisticated fields. This is brought to you by allLogairthmsEqual, the non-profit mathematics channel. Thank you for watching. And so for our bonus theorem today, we'll actually be studying the Pascals Theorem. Now this is something originally proved around 1822 by a certain French official who evidently had served under Napoleon in the invasion of Russia. But basically what it's stating is that if we have one conic, or conic section, often it is drawn as an ellipse of some sort, and it is actually within a second one, actually a second conic section. Obviously this isn't the best picture of two conic sections, but I did the best I could without a... But my idea, actually this isn't my idea, but this is the Pascals Theorem. It's basically stating that there is in fact an infinite number of polygons, like this one, approximately, which are both circumscribed about this inner conic section, and they are inscribed within this larger conic section. So we're considering this idea where there's a polygon such that is true, where basically all of its vertices lie on this outer conic section, and basically it encloses or circumscribes this inner conic section. And in fact, the Pascals theorem is that there is an infinite number of such polygons, and in fact all of those polygons have the exact same number of sides. Now, isn't that amazing? What it's really saying is that there is only one kind of polygon which satisfies that condition, and that is the Pascals theorem. Thank you very much for watching. More is on its way. I plan to release a video on Pascal's triangle, and then perhaps complex exponents. So thank you for watching.